All right, so now we're looking at section 9.3, looking at the relationship of polarity when it connects with the geometry of a compound. So in chapter 8, we looked at dipole moments and how you can have dipoles among individual bonds between atoms. But just because two atoms might have a dipole between each other doesn't mean that the overall molecule will be polar. Because the best way to kind of think about it is, so think about the geometry um, of the molecule, and then think of which direction or what direction are the dipoles going. So where is it most electronegative? Where is that arrow pointing towards? And you kind of see, so here we have a molecule of carbon dioxide, and carbon dioxide has two oxygens bonded to a single carbon, and the oxygens are the more electronegative atoms, and so therefore the dipoles are going to be going outward towards the oxygens, and since it's a linear molecule, the outward pull towards one oxygen is canceled by the outward pull to the other, and so therefore the overall dipole moment for the molecule is equal to 0 because they basically get canceled out. So this overall molecule, carbon dioxide, is a nonpolar molecule. So when we look at water instead, so water, the molecular geometry is a bent shape, and the oxygen is the more electronegative. So the electronegative dipoles are pointing towards the oxygen in the molecule. So therefore, the dipole does have a direction. There's one portion that has a more negative end, and the hydrogen ends are the more positive, and so therefore, water is a polar molecule. So basically, you have to add up the individual bond dipoles to then determine the overall dipole moment for the molecule. So let's look at a couple other ones here. So we have hydrogen combined with chlorine, and that is a polar molecule because basically the chlorine is pulling the electrons towards itself. But then you've got the carbon with 4 chlorines on it in a tetrahedral molecular geometry, and since all the chlorines are going to be pulling equally, the overall charge is, or the overall dipole moment for the molecule is nonpolar. And then for ammonia, since the shape is trigonal pyramidal, all the hydrogens electrons are kind of being pulled towards the nitrogen, and shape-wise, it's going to be a dipole, a negative dipole towards the nitrogen. So hopefully this kind of gives you a better idea of what's going on when you take the individual dipoles that we were looking at in chapter 8 and then applying them to the three-dimensional shape of a molecular geometry. And that's it. I will not be in class tomorrow, but you'll just work on some problems related to